Hi guys, welcome to a new video about embedded DSP design on FPGA. Today's video is going to be a continuation talk about bandpass sampling, but this time about the challenges of implementing bandpass sampling. Meaning, if you have an IF frequency as we talked last time of 10.7 megahertz and a bandwidth of 200 kilohertz, and you were given the choice of a sampling frequency of 10 megahertz and 1 megahertz or 15 megahertz, which sampling frequency will you go for? So apparently all these sampling frequencies, they fit the requirements we discussed last time as per these two equations or two formulas we have in front of us. So all these FS 1 megahertz, 10 megahertz, 15 megahertz, they all meet the requirements for sampling this 10.7 megahertz IF frequency. However, there's a challenge here. The first challenge is when it comes to designing an anti-aliasing filter, you want to have some flexibility designing that filter. You don't want to have stringent requirements on that filter. You want to have some flexibility, and I will explain more what I mean by that. And the other thing is you would have to consider the harmonics generated by the ADC itself, and you don't want these harmonics to pass through your into your bandpass. I mean the spectrum of interest you are interested in. So if you stick around in this video, I will explain more about these challenges and how to make sure we select the right sampling frequency for our system. This is a really challenging topic, and unfortunately I don't know why it gets overlooked, but it is really challenging, and you know it till you see it, because I've seen it, and it's not sometimes you discover these things too late in the design process, and it would be too costly to go back and fix it. So let's start again and see what I mean by the challenges of bandpass sampling. So let's start. Let's say we're going to sample this IF frequency with 1 megahertz, and what's going to happen. So when you sample a certain IF frequency with a certain sampling frequency, you get images, and these images follow the formula or the equation you see in front of us. So the frequency, the image frequency, is always equal the absolute value of the input frequency minus a multiple of the sampling frequency. So for the case of an IF of 10.7 sampled at 1 megahertz, so this IF will aliases to 0.3, and our spectrum will extend from 0.2 all the way to 0.4 with a center frequency of 0.3. However, we will have images, and the image frequencies are the ones we see in front of us, 0.3, 0.7, all the way to, I just listed up to 20 megahertz, but there's more, of course. So anyways, our center frequency is 10.7, and the two closest tones to it are 10.3 and 11.3. 10.3 and 11.3 are images. So 10.3, when you sample it with 10 megahertz with 1 megahertz, it will aliases to 0.3, and same will the 11.7 megahertz. It will aliases to 0.3 once it's sampled with 1 megahertz. So this is not something we want. So we want to make sure we design an anti-aliasing filter that keeps all these image frequencies away from our bandpass. So unfortunately 10.3 is really close to 10.7, our center frequency. So if you sample, let's say just a little bit further, if you sample 10.4 megahertz, then this 10.4 megahertz is assuming just a single tone. It's not a bandwidth limited signal, it's just a single tone. So this single tone will be alias to 0.4, which is our bandpass, which is going to interfere with our signal, and we can hear noise or distortion in our system. So how much distance we have? We have only about 200 kilohertz of margin to 10.6, the lower edge of our IF. So same thing goes to 11.2. So when you sample a frequency with 11, when you sample 11.2 megahertz with 1 megahertz, it's going to alias to 0.2 megahertz, and that's again at the lower edge of our passband. So in this case, we have 400 kilohertz of margin from 10.8, our IF. So in both cases, on the lower side, we have 200 kilohertz from the lower edge, as you can see here, and on the upper edge we have about 400 kilohertz. So if you want to go with a sampling frequency of 1 megahertz, then you would have you may have some challenges designing a good anti-aliasing filter, because the edges has to be really sharp enough to reject 10.4 and reject 11.2. Otherwise, these tones or any signal that happens to land at these areas will just slip into our passband, which is in this case the IF passband. So probably 1 megahertz is not a good sampling frequency, at least at this point. So if you go and sample with 10 megahertz, what's going to happen? So with 10 megahertz we get, so with 10 megahertz for an IF of 10.7 is going to alias to 0.7, and the images we have closer to our passband, to our center frequency of the IF, is 9.3 and 19.3. So meaning now 9.4 megahertz with alias to 0.6. So that's at the border, lower edge of our passband. And in this case, we have a margin of 1.2 megahertz, like what you see here. So it's quite far. So that's would give soften the flexibility, soften the requirements on designing the anti-aliasing filter. And on the upper edge, we have 19.2 megahertz, which aliases to 0.8, which is the upper edge of our IF once it's down converted. So that gives us a margin of 8.4 megahertz from the upper edge, as you can see here. So it's not too bad if you are given the choice to choose between 10 megahertz sampling frequency and 1 megahertz. At this point we can see that 10 megahertz is way better. Okay, so let's say if we go with a sampling frequency of 15 megahertz, what's going to happen? So the images of 15 megahertz are 4.3, 10.7, 19.3, and so on, all the way to 40.7. So at the same time, you have to mention that when you sample an IF of 10.7 megahertz with 15 megahertz, your IF will aliases to 4.3 megahertz. So we have to keep that in mind. So therefore, 4.3 a tone. Let's say if we have a 4.3 tone in our system, that 4.3 is it's just gonna collide with our IF and cause distortion. So you want to make sure in this case you filter out that 4.3 before you pass it to the ADC to sample it. So one of the edges will be of the filter will be 4.3, the lower edge. So in this case you have a margin of 6.3 megahertz away from 10.7 away from 10.6, because we have a bandpass, we have an IF that extends from 10.6 to 10.8, and we want to make sure we keep it clean. We don't want any interferer to be close to it. So if you want to make sure keep 4.3 away from that, then you would have to design your anti-aliasing filters so that 4.3 doesn't get picked up. So anyways, at this point you have a margin of 6.3 megahertz away from the lower edge. On the upper edge, you have a margin of 10.8 megahertz. How is that? Because the closest one is 19.3 megahertz, and its aliases to 4.4, which is the upper edge of our IF. So in this case, you have a margin of 8.6 megahertz. So as you can see, if you compare 15 megahertz sampling frequency with 10 megahertz sampling frequency, of course 15 megahertz is way better. So if you rank them and you would ask yourself who is the winner here, so yeah, definitely you can say the winner in this case among these three options is 15 megahertz. However, this is not enough. You would have to be really careful again. So as I said, the ADC or even the mixer itself have non-linearities, okay, and this introduces harmonics. and then you would have to look at these harmonics where they are going to land once they are bandpass sampled. So let's take a closer look again at the three cases and see how these harmonics translates once we do our bandpass sampling. So for the case of 1 megahertz, these are our harmonics. First, I put all the way to 9 harmonics, as you can see in front of you. And these harmonics, unfortunately, as you can see, once they are undersampled, they alias to, like for the first case, we expect our center frequency to be aliased to 0.3, which is the fundamental 10.7. And you can see the second harmonics get aliased to 0.4, just 100 kilohertz away from it. All of them, like very close. Even worse, the 9th harmonic, it just aliases exactly at 300. Exactly at the center frequency of our fundamental frequency. So definitely designing with an FS of 1 megahertz will be problematic, will cause issues, especially if it happens our ADC creates these harmonics. Then the quality of the signal, once it's in the system, it's digitized and it's in the system for processing, will be a challenge, and the quality totally will be totally compromised, and you won't get good quality output. So if you go with the case with let's see 10 megahertz, so the harmonics of 10 megahertz, as you can see in front of you, not too bad actually. You can see 1.4 megahertz, we have about 0.7 away from the center frequency, so it's not bad. So pretty much all of them we have a fair amount of margin, so it's not bad. But if you go to 15 megahertz, let's look at the 15 megahertz, the case is quite totally different. So if you go to 15 megahertz, for 15 megahertz the signal will alias to 4.4, okay, so it's 4.3, and you have the 8th harmonic aliases to 4.4, so you have only 100 kilohertz away from the center frequency. So that's probably not a good choice. It's a very bad choice. Actually, even worse, there is the 15th harmonic. Actually, the 6th harmonic aliases to 4.2, only 100 kilohertz away, and 8th harmonic aliases to 4.4, same thing. So all these 4 harmonics are really close to our center frequency. So in this case, even though 15 megahertz performed really well when it comes to designing the anti-aliasing filter, but when it comes to harmonics, it turns out it's a challenge. It probably won't be a good choice. So again, the designer here, when he or she decides to start using bandpass sampling, you'd have to be careful about these challenges. The first challenge is making sure you have enough margin so that you can design flexible anti-aliasing filter. You don't want to have tones that could alias into your passband, and you want to have flexibility designing a cheaper bandpass filter, anti-aliasing bandpass filter. And the second thing you'd have to worry about is the ADC or the mixer's harmonics. So harmonics, as I said, I've seen it in the industry, it's a problem. Sometimes you find out about them later in the process, in the design process, and it would be very costly to go back and fix them. And all again comes down to the selection of I would not say correct FS, I would say suitable FS, sampling frequency. So you can see how the dynamics here, how the trade-offs over here interact with each other. So it's not just one variable, which is the FS, there is more than that. So there is FS that you have to select so that you can design a anti-aliasing filter with enough margin on the sides, and also an FS that would pushes away, or would at least make sure that the harmonics would not land in the passband of the system. So I think this covers what exactly I want to talk about. And the conclusion is that the best sampling frequency is not necessarily the one that simply puts the IF where you want it. You want also the ADC generated harmonics to alias as far away as possible from the desired band. And this is the takeaway from this video. Again, thank you for watching this video, and I plan to maybe sometime this week do a quick demo on system generator about how these parameters interact with each other. If I don't do that, I would post another video sometime next week, because this topic I want to talk about it a long time ago. It's the DDC, digital down converter, before we implement our FM receiver. I think DDC would be the last but not least DSP block I would have to consider to discuss before I move to the full implementation of the FM receiver on the FPGA. So I really hope you guys enjoyed this video and you like it and you learned something from it. And at the same time, I highly urge you guys to share this video with your friends and subscribe and hit like so that this video can reach as many students and younger engineers as possible, so that a lot of people benefit from it. Thank you and good luck. Bye.